Hello everyone, I once again welcome you all to MSP lecture series on interpretative spectroscopy. In my last lecture, I started discussion on nuclear spin and transitions and how energy levels varies with the different nuclear spin values. Let me continue from where I had stopped. So, you can see here with nuclear spin I equals half, we have two energy states here, and plus half state is low in energy and minus half is in high in energy, higher energy, and they are represented with downward arrow indicates minus half value, whereas upward arrow indicates plus half value. The gap, whatever is their distance between them, is delta E equals h nu. So, this one can obtain directly from gamma B naught over 2 pi. So, one can get this information nu directly from gamma B naught over 2 pi. So, where B naught is the magnetic field strength and gamma is gyromagnetic ratio. The magnetic field of the spinning nucleus will align either with the external field or against the field. You can see here this arrow represents this is aligned with the magnetic field. So, those nuclei which are aligned with the applied magnetic field, they will be lower in energy, and those which are against the field are opposing the applied magnetic field, they will be higher in energy, they will be having downward arrow. So, a photon with the right amount of energy can be absorbed and cause the spinning proton to flip. When we know that this gap, if we apply the right amount of energy that matches this value, then what happens? Flipping of proton or nucleus takes place. The difference in energy between two spin states over a varying magnetic field I have shown here. You can see as magnetic field strength increases, the gap increases. When the gap increases, energy required will be very high. In that case, what happens? The chemical shift, that term I will be introducing later, the chemical shift difference between the different nuclei in the same molecule would increase. As a result, the spectrum will be well resolved and understanding various functional groups and other groups present would become very easy. This is the advantage of increasing the field strength. So, now let us look into the energy associated with this nuclear transition and magnet strength. As I said, the energy difference is proportional to the magnetic field strength. The energy difference between the two nuclear spin states is directly proportional to the magnetic field strength, and that is given by this equation. H nu equals gamma h B naught over 2 pi. Of course, h cancels and it is simplified, nu equals gamma B naught over 2 pi. So, gamma is gyromagnetic ratio, is a constant for each nucleus, and for hydrogen it is 26.753 radians per Tesla per second. And of course, if you have difficulty in understanding the magnetic field strength in Tesla, 1 Tesla equals 10,000 Gauss. And what is gamma? Gyromagnetic ratio is nothing but the ratio of its magnetic moment to its angular momentum. So, in a magnetic field strength of 14,092 Gauss or 2 Tesla, a 60 megahertz proton is required to flip a proton. That means a 60 megahertz photon is required to flip a proton. That means you take a proton in a magnetic field strength of 14,092 Gauss, the frequency you have to apply, that means the another magnetic field you are applying in a direction perpendicular to the applied magnetic field should have a frequency of 60 megahertz. That would cause proton to flip. So, this is low energy radio frequency, that essentially whatever the magnetic field we are applying perpendicular to one B naught or Bi, we call it as, that is a low energy, comes from the radio frequency region. So, what is magnetic shielding? This is very important term when it comes to the utility of NMR in elucidation of the structure of molecules. So, if all protons absorb the same amount of energy in a given magnetic field, not much information could be obtained. As I mentioned, if you consider ethanol, we have CH3 group is there, we have CH2 group is there, and also we have H in OH. If all of them absorb the same amount of energy in a magnetic field, then we would have got a broad signal that wouldn't have really helped us in understanding the different groups present in it. So that means basically what happens, protons in different groups have absorbed different amount of energy for nuclear transition. Why that happens? But protons are surrounded by electrons that shield them from the external field. So that means when we subject a nucleus into magnetic field, we are not subjecting a bare nucleus, and each nucleus is surrounded by electrons depending upon the valence electrons present in that particular atom, and as a result what happens, these electrons would shield the nucleus from the external magnetic field that is applied. In that case what happens, whether the protons would experience more magnetic field or less magnetic field depends upon the nature of the electron density that is circulating about the nucleus. Circulating electrons create an induced magnetic field that opposes the external magnetic field. That means under the influence of magnetic field, the circulating electrons also create another induced magnetic field that always opposes the external magnetic field. As a result, the net magnetic field experienced by the nucleus will be B0 minus the induced magnetic field, if you say Bi. So that means net magnetic field experienced by nucleus is B0 minus Bi. Bi is the induced magnetic field generated by circulating electrons, which always opposes the applied magnetic field if it is in this direction. This is called magnetic shielding. So that can be seen here. So magnetic field strength must be increased for a shielded proton to flip at the same frequency. For example, let us say we have kept a nucleus at 2 Tesla or 14,092 Gauss, and then the electrons would generate a magnetic field, that is induced magnetic field, that opposes. As a result what happens, net magnetic field experienced by the nucleus drops, hence its precision frequency also drops. In that case what happens, we have to use a different frequency to cause flipping of the nucleus. That means here the frequency decreases. That means either we can decrease the frequency of the applied magnetic field, or we can try to balance the applied magnetic field strength to make it what it was before the opposing magnetic field was generated. So two ways are there. So electrons shielded the nucleus. Here electrons are shielded the nucleus, and the shielding proton fields less than 14,000 Gauss, and stronger applied field are compensated for shielding. That means either you can enhance this one, or you increase the field applied by increasing or decreasing decrease the Larmor frequency we used to flip the nucleus. So now the Larmor frequency corresponds to different field strength I have shown here. 14,100 Gauss, it is 60. This is with respect to proton, and in case of 23,500 this is 100 megahertz, and 47,000 is 200 megahertz, 58,700 Gauss it is 250 megahertz, and 94,000 Gauss it is 400 megahertz, and then 1,17,500 it is 500 megahertz. So the different field strength and corresponding magnetic field strength is shown in this slide. And also of course this one little bit more informative. So here I have given for different isotopes, and also their natural abundance, and also the spin, and also gyromagnetic ratio, and also the corresponding magnetic moment here. If you focus your attention on 1H, it is almost 100% abundant, 99.9844. The rest is 2H, deuterium, and I equals half, and magnetic moment is 2.7927, and then magnetogyric ratio is 26.753 into 10 raised to 7 radians per Tesla per second, and 2H very small amount is there, and I is 1, and it is magnetic moment is given, and also magnetogyric ratio is also given here. You can compare here, magnetic ratio is almost 6 times less than that of proton. And then 11 boron and 10 boron we have. As I mentioned, 11 boron we have 81.17% natural abundance, and spin is 3/2, whereas in case of 10 boron it is 18.83, and then spin is 3, and then both of them have different gyromagnetic ratios. That means this is more sensitive and this is less sensitive. Here you can see from this one, and 13C only 1.1% is there, and rest is 12 carbon, that is NMR inactive, and again spin I equals half, and then magnetic moment is 0.7022, and then the corresponding magnetogyric ratio is 6.728 into 10 raised to 7. And then in case of 14N, this is 99.63 percent natural abundance, whereas 15N is only 0.37. That's the reason most of the nitrogen compounds you don't see either 15N because of lower abundance nor 14N because of quadrupolar interactions. And in case of 17, hardly we can come across any oxygen containing molecules exhibiting 17 NMR signals because of very low abundance. In case if you want to study, we have to enrich those samples with 17O. Here spin is 5/2. And then 19F is very important. This is 100% abundant half spin, and then its sensitivity is pretty good, and magnetogyric ratio is 25.179. The sensitivity wise, it's as good as you can see proton here. And 29 silicon, again only we have 4.7%, rest is 28 silicon, and then I equals half, and then a corresponding magnetogyric ratio is minus 5.319 into 10 raised to 7 radians per Tesla per second. And then other one is very, very important. Nucleus, as far as inorganic chemistry is concerned, organometallic chemistry is concerned, and homogeneous catalysis is concerned, this 31P, it is also 100% abundant, and I equals half, and understanding and interpretation of 31P NMR spectra is as easy as proton NMR. I will be discussing a lot of examples of different type of phosphorus containing compounds to make you familiar with the interpretation of spectra of especially phosphorus compounds, and also in combination with other nuclei where you can come across interaction of phosphorus with either carbon, hydrogen, or even platinum, rhodium, etc. And then here gyromagnetic ratio is 10.840. And of course, the list is quite extensive. I have given in the list for most of the elements which are NMR active, no matter what their natural abundance is, I have given here. You can go through this. Those I have mentioned, I have given some Larmor frequencies. Using these values, you should be able to calculate Larmor frequencies for most of the nuclei we have here, which are NMR active. Try to find out Larmor frequencies at particular field and how it compares with hydrogen. That gives some idea about interpretation of NMR spectra and other things running NMR spectra. So you can see here again, it is quite extensive. I have given for almost all elements starting from 1H to here bismuth. And here I have given NMR frequency of 400 megahertz I have considered, and if 400 megahertz is for 1H, the corresponding field strength for various other nuclei can be seen here, and this is an ideal table. Keep it very handy when you are using NMR. 2H is here, you can see 7 lithium is there, 3/2. Lithium is also quite important because we use lithium in many reactions and coupling reactions and other things. In order to see reaction pathways and other things, we can also do variable temperature NMR and understand how lithium is reacting or how lithium is coming out during the reaction. And 13C I have given, for example, 400 megahertz. What is important is 13C shows about 100, almost 4 times, and then if you go for 19F, 19F is 376, and then phosphorus NMR, phosphorus will be 161, and then platinum, selenium. So these are the very important ones. 1H is 400 megahertz, and corresponding for 13C is about 100 megahertz, and then corresponding 19F is 376, and then 31P is 162. Okay. And if you go for 500 megahertz, phosphorus will be about 200 megahertz. So magnetic dipole moment mu in units of nuclear magneton will be given in this equation here, where MP is the mass of a proton. If you want to calculate magnetic dipole moment mu for whatever the values I have given here, what you need is these things. If you know the mass of a proton, rest all are constant, you should be able to calculate. So this is the typical NMR spectrometer here shown. Okay, so the magnet is there, which gives B0 I was telling you. So here the sample is kept in a soft glass container, and then the magnetic controller is there, magnetic field is adjusted here. What you do, the magnetic field you are applying perpendicular, all these things comes in this one, and then the information goes to detector and radio frequency transmitter. From there, so detector will show you about absorption of energy, and then you get the plot here. Very nicely you can get a spectrum clearly depicting the chemical shifts and coupling constants if there are any. And of course, here field strength is increasing. This is values are given in delta chemical shifts, that is ppm. So when you are referring to chemical shift, either use delta or ppm, one of that one will do. So let us look into a simple molecule and look into 1H NMR. So I have given here methanol. So in methanol, I would say these are here more shielded, absorb at a higher field, and here less shielded, absorbs at a lower field. So that means here why it is absorbing a lesser field and why they are absorbing at a higher field can be seen here. So that depending on their chemical environment, protons in a molecule are shielded to different extent depending upon their chemical environment. If you see here, oxygen being more electronegative pulls the lone pair, that is between the bonded pair between H, in such a way that it becomes almost like H plus. So in this case what happens? You don't have really electron density surrounding H that is generating a induced magnetic field opposing. Okay, that means the whatever the magnitude of the induced magnetic field generated is very minimum. As a result, what happens? Whatever the actual magnetic field is, same is experienced by H. In this case, what happens is less shielded. Whereas here, that is not the case. They have, each one is surrounded by electrons are there, and here these electrons generate a magnetic field opposing the applied magnetic field. As a result, they are shielded and absorbs at a higher field. So now let us look into NMR signals. So number of signals shows how many different kinds of protons are present. For example, if you look into 1H NMR spectrum of ethanol, we get 3 signals. When we get 3 signals, that indicates that there are 3 different kind of protons are present. We know that it is because of CH3 group, CH2 and OH. So now the location of signals show how shielded or de-shielded the proton is. First information is how many groups are there, and next one is where they are appearing in the NMR spectrum. The location of signals also indicate whether they are shielded or de-shielded. And then the intensity of the signal shows the number of protons of that type. That means all this vital information you can get it. One is number of signals, and then where they are located, and then what are their intensities. That means basically if we have CH3, CH2, OH, we have CH3 should have higher intensity, okay, equivalent to 3 hydrogen atom, CH2 have little less, having for 2 hydrogen atoms, and then what the ratio of intensity should be 3:2:1. So that information also comes from NMR. So this all this vital information we can get simply by looking into NMR signals. The signal splitting shows the number of protons on adjacent atoms. Now, where they are located, after identifying 3 groups, the relative positions of those groups in the molecule should be very vital to understand the whole molecule. In that case, what happens? The signal splitting shows the number of protons on adjacent atoms. So that would indicate where exactly they are located. So all this information now comes from NMR signals. So one is number of signals, how many indicate how many groups are there, and then the location of this signal shows whether they are shielded or de-shielded. The intensity would show the relative number of protons present, and then the signal splitting shows where they are located, whether they are close to each other, whether they are farther from each other. All this information comes. With these 4 vital information, we should be able to write the molecular structure without any ambiguity. So all this information comes from NMR signals. So now let's look into the NMR spectrum of methanol here. Methanol has 2 types of protons. One is CH3 protons, one is OH proton. And you can see, as I said, OH proton is less shielded and it is appearing here for this one. And whereas methyl protons are more shielded, they are appearing here. And then if you look into the intensity, this corresponds to 3 hydrogen and this corresponds to 1 H hydrogen. So if I take something like this 1, 2, 3, so you can tell very easily. And this is the increasing field strength where they are appearing. So all this information, whatever the 4 points I mentioned in the previous slide, all this information is nicely depicted in this spectrum. This is the strength of NMR spectroscopy. You can see here the signals. This is all three are identical. So that means now all are resonating at same frequency because all are identical, and then this comes at 4.3. This is the value is 4.3 and this is 3.48. So now let us look into tetramethylsilane. In case of tetramethylsilane, 4 methyl groups are surrounded silicon atom in a tetrahedral fashion, and this one is added to the sample. This tetramethylsilane is added to the sample. Tetramethylsilane is abbreviated as TMS, is added to the sample while measuring 1H as well as 13C and also 29 silicon. So since the silicon is less electronegative than carbon, TMS protons are highly shielded, signal defined as 0. So that means here relatively compared to carbon, the electronegativity of silicon is less. As a result, TMS, the protons present in tetramethylsilane are highly shielded and the signal defined as 0. So the resonance where it comes in the spectra is given the value of 0, and we are measuring chemical shifts of rest of the molecules when we are using with respect to 0 value of TMS. So this is used as a reference. So organic protons absorb downfield to the left of the TMS. Most of the organic molecules we come across always absorb energy and they appear left side of the NMR spectrum. That means the Larmor frequency of all of them will be less, so compared to this one, or Larmor frequency is more. Why Larmor frequency is more? Because they are highly shielded. They are less shielded compared to TMS. So now let's look into the chemical shifts. So chemical shifts, whatever the signals I showed you, they are called chemical shifts. For example, methanol, I showed you 2 chemical shifts, 2 signals, one for oxygen bound hydrogen, other 3 for carbon bound hydrogen. So these signals are chemical shifts, are called as chemical shifts, and they are measured in parts per million. And then the ratio of shift downfield from TMS to total spectrometer frequency is the chemical shift. Why we measure and why in parts per million is this unit is independent of magnetic field strength. If I say 3.48 for methyl protons in methanol, whether I measure NMR or record NMR spectrum at 60 megahertz, 100 megahertz or 300 megahertz, it remains same. That is the reason we measure that in ppm. So same value for 60 megahertz, 100 megahertz, 300 megahertz or 500 megahertz machine. Called the delta scale. We call it as delta scale here. We call it as delta scale. So let me stop here and continue discussion more on chemical shifts to make you familiar with different type of chemical shifts and how they are influenced, why we call it as chemical shift in the first place. Okay, this information let's discuss in more detail in my next lecture. Until then, have an excellent time reading on interpretative spectroscopy.